is interested in the slides that I'm showing. So I just spoke to Gautam about whether the slides are going to be put up in some kind of a central location. But regardless of that, if you would like to look deeper into some of the things I mentioned about, one thing you can do is, so there's this systems biology course that I teach every year. So the slides of the systems biology course are available publicly. So the network stuff that I'm talking about is actually forms something like 50% of the course. Okay, so you can actually access this thing. So you just go to my website, which is Sitabhra, and then on the left you would find a pane, and you go down beneath teaching, you would see systems biology course 2017. Maybe there's also 2018. I don't remember whether all the slides are there or not. So you just click on that. It will take you to the web page of the systems biology course, and there all the files that I use. So I take about 30 lectures or so. So the first, I think, the first 2 or 3 lectures, of course, very general, covers all of systems biology. But from the 4th lecture to about, I think, the 19th lecture, this will be all on networks, going sometimes deeper into some of the things which I just barely covered or didn't cover at all. So you could just take a look at those slides. I also had a plan of devoting a separate semi-tutorial on the concept of modules, or how to find communities or modules in networks by partitioning them using various kinds of algorithms. But for lack of time, I am not able to go into it. So I would conclude this series with my final lecture on something which is related to dynamics on networks. Okay, so far in whatever I've spoken about, I've barely touched upon that once you have a network, then what? Okay, so you can look at these interactions, but you're not really looking at the functional aspects of the interaction, or what is it actually that these interactions do to the system. Okay, you're just focusing on, can I identify whether neuron I has some kind of interaction with neuron J. But typically these interactions are dynamical in character, right? So something causes a change in the action of something else. Okay. So you would be interested, for example, to find out about that, okay, so given this network, now if I put in the dynamics, so each of these nodes actually stands for something. They are not just circles on a graph. Okay. So these nodes, for example, can be neurons. Okay. So now suppose I take part of what Pranay taught. So suppose I put in some kind of a simplified model of an excitable cell like a neuron into each of these circles, and I model the connections as synaptic connections. I may be interested to know how does the activity of different neurons change over time as a result of this network of connections. And suppose I take one type of network and then I replace it with another type of network, I might be interested to know how does the collective activity of the network change as a result of the change in the type of network that I have put those neurons in. So this, of course, is extremely interesting area of study, and occasionally you can actually have interactions between dynamics on networks and dynamics of networks. So what do I mean by dynamics of networks? So the network structure itself can change over time. So of course you have seen an example of this earlier. So when we talked about the preferential attachment model for generating scale-free networks, what we were talking about was a model which incorporated this dynamics of networks. So you started with a single node, then you started adding more nodes, more links. So essentially it was the network itself which was evolving. Okay. So this time varying aspect of network structure, that is what we are describing as dynamics of networks. So now we are going to talk about dynamics on networks, where we are interested in what is happening when the nodes themselves undergo some kind of a activation as a result of the interactions they are having in terms of the network. And often the most interesting dynamics comes when you have an interaction between dynamics of networks and dynamics on networks. Can you give me an example of where you would have a interaction between dynamics of networks and dynamics on networks? Anything you can think of? Google search. In what sense is it a combination of dynamics of and dynamics on? Yeah. Right. Yeah. As a node? Node adding. No. But you don't really change anything in the World Wide Web, right? All you are doing is you are essentially accessing certain nodes which already exist in the network. You're not really changing anything, right? Neurons, yeah. Why? So what would be the example of dynamics of and dynamics on? Right. Right. Correct. And what would be the result of, what would be the interaction between these two? I said that the most interesting thing when these are not independent, but when they interact with each other. So how would, or what would link these two types of dynamics? Well, not quite. So you're almost there. So the important thing is, okay, so the answer was neural network is an example of a system where we have both dynamics of networks and dynamics on networks. So dynamics of networks because the connections themselves are evolving. Okay, so the synaptic connections that you have between neurons are not static, but they strengthen or weaken over time. And it's dynamics on networks because at any given point of time, if you assume that the synapses are more or less unchanging, let's say over a scale of a few seconds or so, then you can think of it as dynamics of the neurons which are connected by a fixed network. Okay. Now what connects them together is the phenomenon of learning. Okay. So when two neurons fire together, Hebb rule, which was enunciated by Donald Hebb back in 1949, Hebb rule suggests that the connection between them would be strengthened. Whereas if they fire at very different times, the connection between them would be weakened. So this used to be a hypothesis until till about the 90s, people actually saw long-term potentiation and long-term depression, which is actually the biological basis of precisely that reinforcement. Okay. So that actually provides the link between the dynamics on network and dynamics of networks in neuronal networks. Okay. You could, of course, think of other kinds of examples. For example, when epidemics propagate on networks. Okay. So as the epidemic propagates, people kind of drop out of the network, or people take evasive action. They decided to like stop attending mass gatherings and so on. So gradually, as the epidemic propagates on the network, so the epidemic is of course an example of dynamics on a network, but people taking evasive action by reducing the number of connections that they have would be dynamics of a network. Okay. So again, that would be an example of a feedback between dynamics of networks and dynamics on networks. And this is exciting because just by looking at it as an example of dynamics on a network, where you take a constant or a fixed network and you just study something like SIRS model on this, it will not tell you what will actually happen in the case of a real epidemic, because people are not just going to passively let the epidemic sweep through them. They are going to try to take various kinds of strategic maneuvers to try to avoid it. So of course the network will change over time, and you have to take this account when you are trying to predict that in the case of a real epidemic, how will things pan out. Okay, so what I'm going to do in this final lecture is going to show you an example of how you study dynamics on networks, and I will take the example of ecological networks in most of the things I do, but this is a question which goes beyond ecological systems, and in fact is become extremely important, for example, for economists following the 2007-2008 crisis. I will show you how ecological systems and financial systems connect in a moment. So the question we are going to ask is the following, that are complex systems inherently unstable? And to answer this question, we necessarily have to look at this topic of how dynamics pans out on networks, or if you have each of the nodes being described by some dynamical equations, how this results in the collective dynamics of the entire system. So the question we are asking is the following: how do we understand instability which propagates along complex networks? Now, instabilities which are essentially brought about by the existence of a network, one very common example of this is if you are traveling around India during winter. Okay, so for example, let's say you are traveling from Chennai to maybe Kochi. Okay, so you go to the airport sufficiently early, and then you are told by whoever is checking you in, sorry sir, your flight has been delayed by weather. So you look out of the window and sun is shining, it's perfect day, and you say, what weather? So you say, yeah, the weather in Delhi, sir. So the plane which was supposed to come to take you from Chennai to Kochi is apparently supposed to come from Delhi, and it couldn't take off on time because there's fog in Delhi early in the morning, and and then there's a cascading effect. Okay? So essentially what is happening is, although you want to fly from point A to point B, where you see no effect of weather, because this particular link is not isolated but part of a much larger network. So something which happens at point C, which is a very far off point in the network, essentially propagates and starts affecting regions of the network very far in terms of network distance from the original source of this perturbation. Okay. So that's what I mean by instability. So this is a disturbance which normally wouldn't have affected you had you not been connected in terms of this complex network. Its effect only comes about because of the disturbances which are propagating from node to node through the network. Another such example which we are of course familiar with is disturbances in computer networks. Sometimes, for example, it affects the entire internet, where your internet services are disrupted because some submarine cable beneath the Atlantic has been disrupted. Okay? So the entire network traffic between North America and the rest of the world gets affected, and the pages you want to visit start loading extremely slowly. Another example which affects all of us, fortunately fairly rarely, is the large scale failure of power grid. Okay? So this photograph is of course taken from New York, but all of us have been victims of large scale failures of power grid even in India, where typically a very innocuous event initially, let's say some branch falling over a high tension power cable causes a particular line to go down, and then as in a series of cascades, power station after power station withdraws themselves from the grid, and eventually entire regions of India essentially become dark. Okay. And I mentioned that this kind of question has become extremely important for people trying to understand financial systems to kind of solve, because the 2007-2008 crisis, which is considered to be the worst event affecting the international economy after the Great Depression following the crash of 1929, essentially was brought about by financial institutions collapsing in a cascade. So the way it happens is as follows. So you lend out money to various individuals, and you make bad judgments, and at some point some of your borrowers basically come over and say, I'm sorry, I won't be able to pay you back. At that point you are in a bit of trouble, because you yourself have, let's say, borrowed from someone else, and now you can't fulfill your promise. So basically you fold. Okay? You declare yourself insolvent. Okay? Now your problem may be over, but the problem just starts for people who lent you money, right? Because now they are in quandary over how to give money back to their creditors. And so in some cases it could be that your creditor also has to declare insolvency, because there's no way that he or she can satisfy their creditors if you don't pay the money that you owe to him or her in the first place. Okay? So in this way, financial institution after financial institution can fold as a result of some initial event where a few people said that, sorry, we can't pay. Okay. So how is it that these kinds of events happen? Now you might say that, well, if it's a network, then in all probability things like this should occur, but fortunately it's fairly rare. So the question comes about that, why is it that we don't have such cascading events most of the time? And in circumstances where we do see it happen, how is it coming about? Is it because that the network structure somehow has changed in the meantime? If that is the case, could we redesign network structures such that we could make the system robust against such cascading collapses? You could, of course, come up with even more, far out kind of examples of this. So some people view, for example, epilepsy as such a cascading collapse, where brain region after brain region goes into an abnormal state of aberrant activity. So every time each new brain region, goes into this kind of a high state of activity, it of course triggers other neighboring regions to go into high state of activity. So even epilepsy can be viewed as such a cascading effect. And finally, historians who study rise and decline of civilizations have recently tried to see it as a cascade of events which eventually trigger, for example, the collapse of entities like the Roman Empire. Okay? So the common theme among all of this is that you have a local failure, an initially local failure leading to a global event, namely the collapse of the entire complex systems as a result of propagation of failures across the network. Yeah. So people who are involved in ecosystem management are of course extremely interested in these kinds of questions, because for them it is very much related to how to prevent ecological catastrophe. So for example, if you are confronted with these kind of a food web, okay, so this is a marine ecosystem. So most of the nodes that you see beneath the wavy line correspond to various species of fish. So for example, this is tuna, this is haddock, these are mussels, scallops, squid, and so on. And those nodes which are above this wavy line are basically aquatic birds. So you can see that it's a quite dense network of lines In a few cases, you can even see self-loops. So these are, cannibalistic species of fish which kind of feed on each other, like lamprey and so on. But of course, most of the time you see just, nodes going from one node to another node. And so the question one can ask over here is that suppose because of overfishing or some other reason, there's a sudden decline in the population of, for example, mackerel over here. You would like to know whether this will trigger a decrease, extremely large decrease, for example, in the population of cod, on a population of tuna, and then eventually would it, affect the population of the aquatic birds, which themselves will show a collapse, and could that result in a overall decline in the population of the entire ecosystem with some of the species going extinct. So you'd like to understand, whether a single decline, a rapid decline in population, for example, a single extinction event can actually trigger other extinctions over this entire network. And of course, if you are concerned about the effect of human intervention, so for example, how does fishing affect this entire ecosystem? So should you put in effect a fishing ban for a few months, and which period should you actually impose the fishing ban? So if you are interested in policy decisions like this, you would better be very sure about exactly what effect those interventions have on such a complex network. And sometimes you are interested in even more fundamental question. You could be asking, is higher diversity, or does having more species interacting with each other very densely, is it good or bad for the robustness or resilience of the entire ecosystem? Now it turns out that although this question seems fairly innocent, and if you ask some people, of course they would say that that's a stupid question. Of course diversity is good. In fact, the entire Green Party platform is based upon that premise, that higher diversity, higher connectivity between species is always good for the ecosystem. It turns out that when you look at this question as a scientist, it's not so cut and dried. In fact, this relation between complexity and the stability of the complex system has been a bone of contention among ecologists and other kinds of scientists for a fairly long time. So when I say our complex networks are unstable, so first of all I have to make sure that we are on the same page about how we measure complexity. So when I say complex, I mean that a more complex node has many more number of nodes, and or a higher density of connections, and or a greater diversity of interaction strengths between the various nodes. Okay. So in terms of numbers or symbols, I could say that my complexity is measured in terms of n, the number of vertices of the graph, the density of connections. So this is basically your k by n, the average degree by number of nodes, so which is essentially nothing but your connection probability. And this is a new quantity for you. This is something that I have not introduced earlier. So this is basically saying what is the diversity of interaction strength. So suppose you have each link associated with some weight. Let's say that between nodes I and j, you have a weight w sub ij. So I'm saying that if wij is assumed to be from some distribution, what is the width of this distribution? What is the variance of this distribution? So that gives me an idea of how diverse are the interaction strengths. Okay. So the question turns out to be not settled as some people like to believe, but in fact it's a long-standing puzzle that most of the theoretical work done on this question seems to imply that as you increase any of these or all of these, they would tend to decrease the stability, whereas observations by field ecologists sometimes seem to suggest the opposite. Now, this is a kind of a loaded statement, it's sometimes very difficult to interpret the observations done by field ecologists and say, is it saying complex networks are stable or unstable? Okay. So that's why I say that sometimes they seem to show the opposite. Okay. Sorry? I'm sorry. Yeah, I'll come to it in a detail in the next 2 slides. So this is just to pose the problem, and then I'm coming to detail. Okay. So what is the field ecologist view? Okay. So the field ecologists, at least the bulk of the studies, seem to suggest that diversity, that is the larger the network, the more diverse it is. Diversity is essential for maintaining network stability. Okay. And this is essentially based upon or started from the pioneering field work of this ecologist Charles Elton, who in the 50s wrote a very influential book summarizing years of studies across very different ecosystems, and he summarized his results in a single sentence. He said, based upon my studies, it seems that simple ecosystems are less stable than complex ones. So he based this statement on the following set of observations. So he said that, look, if you look at simpler communities, and when he says simpler communities, it just means that there are fewer number of species. So if you look at it in terms of networks, it means that there are lesser number of vertices. So in simpler communities, populations show much larger fluctuations than more complex communities. Okay? And if you have large fluctuations in populations, it is quite likely that at some point, when you have a dip in population, it will hit the boundary imposed by the alley effect and go extinct. Okay. So consequentially, simple communities are much more likely to experience species extinctions. If you look at cultivated land, which by definition is extremely low diversity, typically you have monoculture, right? You take a field, you take out all the weeds, okay, and you only plant a single species. Okay, so by definition, this is a single species ecosystem, and that is very susceptible to invasion by foreign species, invasion by pests, okay, as compared to like a rainforest where you have lots of different species interacting with each other. So insect outbreaks are fairly rare in diverse tropical forests, but they are much more common in less diverse subtropical forests. Okay. So based upon this, he said that the less complex a system is, the more unstable it is, that the more likely that some disturbance would essentially take it out of whatever state it is in. Now a theoretical ecologist, again a very famous one, Robert Macarthur, so his fame lies in coming up with this whole scaling laws of island biogeography. He tried to provide some kind of a theoretical structure to explain why this could be the case. So if you look at the explanation, it's a bit like invoking insurance in some sense. So what do I mean by that? So suppose you are getting into the insurance business, you want to diversify your client base as much as possible. You don't start your insurance business by first selling insurance to all your family members. Why is that? Why is, if you are an insurance agent, why is selling insurance to your immediate family members and only to your immediate family members does not make good business sense? Good point. Anything else? Yeah, that's a very good point, that if there's a hereditary disease which makes the family members more likely to die early, you would of course be in trouble with the insurance company. But there could be another event. They could all be in the same marriage ceremony when the wall collapses, when the ceiling collapses. Okay, so you would have to pay out the insurance to everyone essentially. Okay, so Macarthur said that, look, if I am a species, it behooves me to diversify my origins of food as much as possible. So if I just depend upon one species, so if I'm like a panda and I just only eat green shoots, bamboo shoots, okay, if something happens to bamboo, like suddenly bamboo becomes very rare in the region, I'm likely to go hungry. Okay, I'll starve, and essentially the population will collapse. So instead, if I can have bamboo as well as let's say mushrooms, or let's say I start feeding on ants or something. Okay, so now I've diversified my food sources so much that I would be able to now live even if one or two of my food sources, the species on which I depend upon, go extinct. Okay, and so therefore this means that if I have more connections, I am much more likely to survive local extinctions than if I only have one or two connections. Okay. Now, this seemed to be fairly satisfactory till about the 1970s, when first a numerical simulation based paper by Gardner and Ashby suggested the opposite. So their numerical experiments on the stability of randomly constructed networks seem to suggest that the more complex a system is, that is, the more number of nodes there are, the more connections there are, the more likely that it was to collapse, followed in 1972 by a very rigorous analysis done by Robert May, whom I mentioned in the previous class, where he showed using mathematical arguments why this would in fact always be the case. Yeah, sorry, question there?
So how would we define simpler communities in this example? Simpler communities?
Right. So simpler would typically mean either the number of nodes is fewer and / or the density of connections is low. So if you have two networks which have roughly the same number of nodes, in one case if there are very sparse connections, in the other case if there are very dense connections, then the one with the more dense connections you call more complex, and this one you call simple. Okay. So these sets of results essentially suggested that as you increase network size, connectivity, interaction strength, typically that results in a decrease in stability. Okay. So therefore, the theorist's view as opposed to the empiricist's view is that increasing diversity leads to network instability, and this is the basis for what is known as the stability diversity debate, which actually has continued to this day in the ecological literature. Okay. Now, if you look at the theoretical argument of May, which I will in fact go through in a few slides, you would realize that there is nothing inherently ecological in those arguments. So you can pretty much take the arguments he has and apply it to other kinds of systems, namely like financial systems. In fact, in about 2006 or so, May, along with two other ecologists, Levin and Sugihara, had actually written an opinion piece in Nature called Ecology for Bankers, okay, where they suggested that the international banking system was becoming so hopelessly intertwined. So, you had banks in Europe, lending out to banks in Asia, which in turn was, lending out to banks in the United States and so on, that you had an extremely complex network of dependence between financial institutions worldwide. And so therefore, a perturbation event at any bank could actually trigger large scale perturbations in the entire financial systems. And so therefore, bankers should maybe study ecological stability in order to be aware of the possible weakness of their entire system. So this turned out to be prescient because this was just before the big 2008-2009 event. And in a sense, if you look at the theoretical argument, you find that it pretty much applies to almost any complex network that you can think of. Okay. Okay. So at this point, you might say, okay, why are we, debating over this when the simplest thing is basically just to do an experiment and figure out who is right. Okay. And there have been attempts. So the largest scale experiment that have been carried out has been done in the Cedar Creek National Park, United States, where David Tillman's group essentially has over a couple of decades been going every year to a certain set of designated patches where they have sets of patches each having a different number of plant species in them. So every year they go and obtain samples so that they can estimate the total biomass in each of these patches, and they like to see whether you can relate the amount of biomass present in the system to its diversity. There was also a perturbation event in this system which was entirely unplanned. So there was a extremely bad drought which happened on one of the years, which essentially resulted in many of the species dying out. So this provided a natural experiment where you try to see, okay, those patches which had a much larger initial diversity, do they recover faster than those patches which had a lower diversity? So you can also look at the effect of diversity on the ability of a system to recover following a large perturbation. So it does turn out that in terms of biomass, there is evidence that if you have more species in a particular patch, they do seem to show a higher total biomass. So this is year by year, so I'm just showing like quite old data. So this is 97, 98, 99, 2000. So you can see that in general it appears that if you have a higher diversity in your system, you also tend to have a higher total biomass. Also in general, it seems that if you looked at how quickly a patch seemed to recover from the drought event, that seemed to correlate fairly well with the initial diversity of the system. Okay. But if you look at the population variability of the system, so if you look at how the population of individual species depended upon the diversity of the patch, there seems to be not much of a correlation. And both this effect, the resistance to drought, and the earlier event, which is this higher total biomass, could have alternative theoretical explanations. People have shown that it could be just averaging effect. So you have a larger number of species. So when you average over those larger number of species, things smooth out much more than if you have fewer number of species. So it just happened that by stochastic fluctuation, you had lower biomass in patches which had fewer species, and you should not conclude from that there is some kind of a solid reason as to why higher diversity would lead to better survivability of the patch. Now there have been lots of complaints about Tillman's experiment that it's not really controlled. As you can see, it's open air, right? So there's no way they can control what is going in and what is going out of the ecosystem. They would only like come for a week or so in every year and collect samples and so on. So if you are very rigorous about the kind of experiments you want to do, you are very dissatisfied. So at the other end, people have tried to set up this bottled ecosystem experiments. So these are called ecotrons. So the initial ecotron experiments used to be done in the United Kingdom. Currently, the ecotrons have been set up in Montpellier in France. So these photographs are from the current ecotron experiments in Montpellier. So what they do is they have large enclosed chambers in which they would put in few species. So they could be of different types. So they could be, of course, plants. There would be a few microorganisms which essentially function as decomposers of the detritus of the dead species. There would be insects which feed on these plants, and there would be other insects which feed on these herbivorous insects. Okay. So you can change the diversity, so you can have more nodes or less nodes in different chambers, and then you can study what happens over time in each of these chambers. Okay. Now, turns out that these kinds of experiments are extremely hard to do, because most of the time what happened, at least in the initial phases of these experiments, was that they would take a few species, some decomposers, some plants, some herbivores and some predators, put them in a chamber, enclose it completely. So essentially it's completely isolated from the rest of the environment. So the sunlight is essentially provided by these lamps, and they have artificial winds set up with fans and so on. Okay. So they would have this completely isolated systems, then they would start the experiment, and within a few days everything died. Okay. So the whole ecosystem collapsed. Okay. So it turned out that it was extremely hard to work out exactly what proportion of species to put in, and how many species to put in, what species to put in order to make sure that it will even survive beyond a few weeks. Okay. But occasionally they would succeed, and they would collect data from that, and that seemed to suggest again that higher diversity communities are more productive than low diversity ones. So here they are showing, for example, the percentage change in the vegetation cover as a function of time, and the three curves corresponding to high diversity, medium diversity and low diversity. So you notice that after some initial transients, they seem to settle down to the high diversity plots or high diversity model ecologies seem to have a higher percentage change in vegetation cover compared to the lower diversity ones. Less clear is the consumption of carbon dioxide, but again it seemed that higher diversity ones have a very different patterns compared to lower and medium ones. But again, it's not clear how this will scale over to real communities, because as I mentioned, there were lots of problems with these kinds of experiments where most of them collapsed very quickly, and the few which survived, you don't even know whether they actually mimic what you see in reality. On the other hand, if you look at the theoretical arguments, they're actually fairly simple to understand. Okay. So this essentially illustrates the theorist's view that increasing diversity leads to network instability, and what you do is you start with, for example, a simple system of just one predator and one prey. So Malay, of course, next week would go into extremely detailed models for describing such kind of systems. Here I am just showing you the simplest of all possible such predator-prey models. This is just the Lotka-Volterra model. Okay. So suppose you have a Lotka-Volterra model describing the interaction between one predator and one prey. So I'm assuming most of you are familiar with Lotka-Volterra. If you are not, let me just spend 1 minute explaining what it is. So if you say that X is the population, or let's say the population density of a prey species, let's say grass, and Y is the population density of a predator species, let's say sheep, you're asking how does the population of prey and how does the population of predator change over time. Now of course, as the sheep start grazing and eating the grass population would come down, let's say, but of course grass grows over time. So you have a term which basically stands for the growth, the increase in the population of grass, and then this term basically says that the bigger the sheep population, the more the population of grass reduces. Okay? So this is the growth part, and this is the decay because of predation. Now for the predator, you have a growth term which is essentially proportional to the population of the prey species. So the higher the population of the prey species, the more the growth. Okay. But the predator population also dies at a particular rate. So, this tells you how the predator population decays as a result of death. So, if you are interested in questions of stability, okay, what do? You ask what is the equilibrium population of these two species. How do you find the equilibrium? So, you just say that, look, what does equilibrium mean? It means that over time the population has now become a constant, that is, it does not change, i.e. this equals 0 and this equals 0. Okay. So, you just set this expression equal to 0, this expression equal to 0 and solve for x and y. Okay. So, unsurprisingly, you will get then what is the equilibrium solution for this equation? So, x equals d by c and x equals a by b, y equals a by b and x equals d by c, right. So, now that tells you the equilibrium, but it does not tell you anything about its stability. That is, if you have a small perturbation, suppose your system is at that value where x equals d by c and y equals a by b. So, suppose you are at this equilibrium, let us call this x naught and y naught, and now suppose there is a small decrease in the population of the plant species. So, x instead of being x naught, let us say has decreased by a infinitesimal quantity delta x. Okay. So, what you are interested to know is that how will this perturbation evolve over time. Okay. So, will this perturbation quickly decay back to 0, so that you again go back to x naught, or would the perturbation keep growing and eventually you are completely kicked out of this equilibrium. So, that essentially is what stability is all about. Okay. If you want to think in another way, so you could, for example, view a dynamical system as something like a bowl, which could be either placed with its base like this, or it could be turned over and placed like this. And so, now if you place a marble anywhere on the system, in this particular system it just rolls over here and settles down here. So, once it settles down here, even if you give it small disturbances, it just quickly goes back to this equilibrium position. So, this essentially corresponds to the equilibrium. Okay. Now, consider this circumstance. So, here if you are extremely careful, you can just place a marble exactly at the apex of this bowl, and provided you do not disturb it and there are no air currents and so on, it would remain there, but the smallest gust of wind would make it fall over. Okay. So, this would correspond to a stable, whereas this would correspond to a situation of unstable equilibrium. Okay. So, how do you find whether an equilibrium is stable or unstable? So, had it been a simple system like which is described by just a single differential equation dx dt equal to f of x, okay, and you are saying that, look, I am interested in the stability of x naught such that f x at x naught goes to 0, how do you find the stability of this system? Sorry? So, you would say that, okay, one of the simplest things I can do is, so what am I interested in? I am interested to know whether f x plus delta x, how does this behave, right? So, the simplest thing I can do is I can do a Taylor series expansion about x naught. Okay. So, if I do a Taylor series expansion, I can write it as f x naught plus del f del x times delta x, where this derivative is obtained around x naught. Then I can get, well, okay, sorry, this is just a single variable, right? So, I can just write it as df dx. So then I can look at the second order derivative and delta x square and so on, right, and higher order powers. Okay. So now suppose you are interested in extremely small perturbations. So delta x essentially can be taken to be going towards 0. In which case you can say that compared to delta x square is very small, and of course delta x cube would be even smaller. Okay. So at that limit I can actually ignore all terms except for the term proportional to delta x. Okay. Now what is fx naught? By definition of equilibrium, this is 0, right. So essentially whether my perturbation will grow or decay depends pretty much on just the coefficient of delta x, which is simply the derivative of f with respect to x at x naught. Okay. So if this coefficient is positive, that is if the derivative is greater than 0, that means it will grow, else it will decay. Okay. Because if it is a positive quantity, I can write this equation as basically that some ddt of delta x equal to some positive constant into delta x, which means it exponentially grows. On the other hand, if it's a negative constant, it means ddt of delta x is equal to some negative quantity times delta x, which of course means that it will decay exponentially. Okay. Is that clear? If it's not clear, please feel free to ask me. Okay. And so therefore, the stability of the system of the equilibrium x naught is just given by the condition df dx at x equal to x naught. So if it is less than 0, this implies that it is stable. If it is greater than 0, it implies that it's unstable. Okay. So for a system described by a single differential equation, it's fairly easy. It's just high school calculus. What happens if you have two coupled differential equations? So since now you have to not only look at x and y in isolation, but also the effect of y on x and x on y, not surprisingly you have to look at a matrix. Okay, so it's not a single derivative that one is talking about, but a matrix of partial derivatives. Okay. So what you do is you say that, well, suppose I have dx dt described by f of x and y, so it's a joint function of both x and y, and dy dt is a joint function of x and y. So now my stability will given not simply by df dx and dg dy, but rather del f del x, del f del y, del g del x, and del g del y. Okay. So this matrix, for historical reasons, is known as the Jacobian matrix of the corresponding system of differential equations. Okay. So what you're doing is you're simply generalizing whatever you did for a single differential equation, and you say that, look, once I have more than one variable, it's no longer possible to just talk in terms of the slope of a single variable. I now have to say how does the slope of each of these functions look with respect to all the different variables, and so that's how you come up with this matrix. Okay. So if you have more than two, you would now have that many more entries in this matrix. Okay. So if you had a third variable, so if I now impose, let's say, dz dt, which is, let's say, h of x, y, and z, okay, so then the corresponding Jacobian would simply be a 3 by 3 matrix, which goes like del f del x, del f del y, del f del z, del g del x, del g del y, del G, del Z, and then del H, del X, del H, del Y, and del H, del Z. Okay? So you can easily generalize to any number of coupled differential equation that you want. Okay? So you can always find the stability of their equilibria by evaluating the Jacobian. And now what do? Because it's a matrix, I have to find out the eigenvalues of this matrix and ask whether those eigenvalues are positive or negative. So that will tell me about whether the perturbations will grow or decay. Okay? So what I am doing essentially is I am looking at the perturbations and I am decomposing them into various eigenmodes, and I am asking, are any of the eigenmodes growing? If any of the eigenmodes grow over time, that means that the equilibrium would be unstable. Okay? And so that is what you do over here. So you take the Lotka-Volterra system, you compute its Jacobian, and you ask, are its eigenvalues both negative, or is at least one of them positive? If any one of them are positive, or if both are positive, then that would mean that the corresponding equilibrium is unstable. Okay? So the condition essentially boils down to asking, is the real part, okay, so why do you say real part? Because in principle in some systems you could have complex eigenvalues. So you want to take that into account. You say that is the real part, largest real part of the eigenvalues negative. Okay? So if the largest real part is negative, of course it means all other eigenvalues, real parts, would be negative, and so therefore they will all decay. Incidentally, if I mention complex eigenvalues, so suppose I ask you that you have an eigenmode which corresponds to a complex eigenvalue, what kind of, so it has a negative real part and an imaginary part. So what kind of behavior would the perturbation show? Can you guess? Sorry? Oscillations, but what kind, right? Because I said negative real part. So it would decay, but in a decaying oscillation manner, right? And similarly, if you have a positive real part, but imaginary part, so that means it would grow, but it would decay in a oscillatory, it will increase in an oscillatory manner, right? Correct. Okay. So what May showed was that if you now start looking at larger and larger systems of coupled differential equations, so you start coupling more and more differential equations, then the probability that the largest eigenvalue will become positive essentially starts coming closer and closer to 1 as the system size increases, or the connection density increases, or the interaction strength increases. Okay? So this is just to tell you very quickly the result. I will actually work through the entire argument in a couple more slides. So if you just go back and look at his article, the 1972 article, again I mentioned that really great paradigm changing work can often be described very simply. If you go and look at his paper, it's a one-page paper in Nature, just one page. Okay? And it basically completely changed the world of ecology. Okay? So, and the arguments are actually fairly simple to understand. So anybody could have made those arguments before May, but nobody had done it, okay? Because you need to come at it with a certain perspective. So let me just walk you through the set of arguments slowly. Okay? So how did May actually come up with this argument? So what May is saying is that, all right, you can take any ecosystem and its state at a particular instant is specified by the populations of each of the species which belongs to it. Okay? So if I say that xi is the population of the ith species, I can describe the state of the entire network as just this vector whose components are basically x1, x2, x3. So the population of the first species, population of the second species, population of the third species, up to population of nth species. Okay? I have of course written it in a much more general form where I say that xi is the state of the ith node. That's because I'd like you to appreciate that this is nothing ecology specific. You can take it to your favorite dynamical system, which can be described by a set of coupled differential equations, and just write it exactly in this form. Whenever you can describe the state of each node in terms of a variable, you can actually write down the state of the entire network in terms of a vector like this. Okay. Now, because it's the dynamics you're interested in, you can then say that, look, the time evolution of each of these variables are described by differential equations. So, I write down the corresponding dynamical systems as, let's say, dx sub I dt fix. So, if you're interested in ecology, for example, these f's would essentially take the form of a Lotka-Volterra equation. If you're interested in something else, you would change it with that something else. So, for example, if you're doing neural network, for example, you would be, for example, putting in something like something like a Hodgkin-Huxley or whatever. Now, suppose you're interested in the fixed point equilibrium of the dynamics. So, then you can solve for these equilibria by setting each of these f's to 0, and by doing that you can get each of the equilibria, which I represent a typical equilibria as simply x naught. Okay. Now, as before, the local stability of x naught can be obtained by linearizing about this equilibrium. So, you're interested in this disturbance delta x, okay, which is simply the difference between the equilibrium and your current state. And you can study how this perturbation grows or decays with time simply as a differential equation which describes the time evolution behavior of the delta x. So, by doing a linear stability analysis, it simply becomes ddt of delta x is the Jacobian times delta x. So, essentially what I am doing is I am just rephrasing whatever I have shown you with the respect to Lotka-Volterra in terms of a matrix equations. Okay. So, is this clear to everyone up to this point? If it's not, just let me know. Okay. Okay. Now, as I mentioned, the stability of the system is given by the largest eigenvalue. So, you can write the long time behavior of the perturbation as simply the exponential of the largest eigenvalue times t. Okay. So, if this largest eigenvalue is positive, that means this perturbation will grow exponentially. If this is negative, that means this perturbation will decay exponentially. And so, therefore, you say that the condition that the equilibrium is stable is simply that the largest eigenvalue is negative. Okay. So, now when you are dealing with general systems, the question you ask is, what is the probability that for any given network this largest eigenvalue is negative? Okay. Now, this is the point. Up to this point, it's pretty much what you would have found in any dynamical systems textbook in the 1970s. From this point on, May's contribution starts. So, he says that, all right, let's assume that in isolation each variable is stable. Okay. Because I am interested in, or May is interested in, whether the network can induce instability. If the nodes themselves are unstable to begin with, even if you put them in a network and they are unstable, it's no big deal, right? So, he says that suppose each of the nodes are stable to begin with, can connecting them in a network lead to instabilities? That's the question. And so, therefore, he assumes that each node is independently stable. So, this means that the diagonal elements of the Jacobian will all be negative, right? Because it's the diagonal elements like del f, del x, del g, del y, del h, del z, which tells you that if there is a perturbation in a particular variable, whether that particular variable will become unstable or not, even if all the off diagonal terms were 0. Okay. So, suppose you go back to the Lotka-Volterra system and you say that I am primarily interested in whether, so let us say you write del x del t equal to, so you had this, right, ax minus bxy and del y del t equal to minus dx, dy plus cxy. Okay. So if you didn't have any interaction between them, this would essentially boil down to just this system. Okay. And so you are imposing the condition that in isolation, each of these systems would be stable, which essentially means nothing other than saying that the diagonal elements, so in the case of Lotka-Volterra, the diagonal elements would be a and minus d. So you are just saying that all of these terms would be negative. Okay. Now, since what these diagonal terms do is just give you a time scale at which the perturbation decays. No. So if you look at this e to the power lambda max t, what is this doing? So it's providing a time scale, right? How quickly does the perturbation decay? Okay. And so therefore, since you are free to choose your time scale, you can just set it equal to 1. Okay. Nobody says that you have to measure in the scale of years. It could be, any unit that you decide. So you just put it to 1. Okay. And so therefore, now you have a matrix all of whose diagonal elements are minus 1. And so therefore, you can rewrite the Jacobian as made out of two matrices. One is B, what B is in a moment, and the other is simply the identity matrix. All elements 0 except the diagonal, all of whose entries are 1. Okay. So your B matrix is a matrix whose diagonal elements are 0, and you have reduced the question from a question about the eigenvalues of A to question about the eigenvalues of B, and because it's B minus I, the largest eigenvalue of A and the largest eigenvalue of B would have a difference of 1. Okay. And so if your question over here was what's the largest eigenvalue of A likely, or what's the probability that it would be less than 0, because you have this subtraction of an identity matrix, you are asking the question, what is the probability that the largest eigenvalue of B is actually less than 1? Is that clear? If it's not clear, just ask him. Is it clear or not? That there's no shame in like saying that this is, I went too fast or something. Is it clear? Okay. So now the really fun part will start. So you have basically reduced the question to one about the probability distribution of eigenvalues of this matrix whose diagonal entries are all 0, and we don't know what the off diagonal entries are. It could be anything, right? Because you are considering all possible ecological systems. So now you have to say that what kind of assumption you have about the off diagonal entries. Now what do the off diagonal entries stand for? They actually stand for the network, because depending upon who you are connected with, the off diagonal entries would be either 0 or non-zero, right? And so here is where the assumption about what kind of network you're looking at comes in. So Robert May started with the simplest assumption, where he said that let us assume that B does not have any particular structure. Okay? In other words, B is a random matrix. So each of the elements are basically chosen at random from some distribution. Okay? So let us assume that there is a probability associated with whether every entry is 0 or 1. So if it has a probability dense distribution, if it has a probability of C, so basically you say that if the matrix B is associated with a network of connectance C, then an element Bij would be 0 with probability 1 minus C. So if you are coming at it from a network perspective, C is nothing other than the connection probability. So the probability that a pair of nodes will be connected. Okay. So for a random network, as we had seen, this is nothing but your average degree divided by n. Okay. So for if you know what network you're starting with, your C is nothing but average degree by n. So this tells you what's the probability that a pair of nodes is connected. So if it is connected, that would mean that the corresponding element of the Bij matrix is non-zero, and so therefore the probability that it's 0 is actually with the probability 1 minus C, 1 minus the connection density, which tells you what's the probability that you will not have a link between two nodes. Okay. However, in networks, you just stopped with the fact that either you have a connection or you don't have a connection. Okay. Either because adjacency matrices are typically having entries 0 or 1. Since the B matrix is related to the Jacobian, which has essentially real numbers as entries, so now you also have to associate a real number with every non-zero entry. Okay. So what he did was he chose each of these non-zero elements from a normal distribution with mean 0 and variance sigma square. So this variance is basically telling you how distributed are your interaction strengths. Okay. So now you see how this relates to the original question you're starting. Your diversity is related to how many coupled differential equations are you talking about. So the size of the matrix. Your connection density, how many interactions you have, is related to this C connectance. And what is the diversity of your interactions is related to this variance of the normal distribution from which you're choosing the non-zero elements. Okay. And at this point, May decided to invoke a wonderful theorem proposed by Eugene Wigner from random matrix theory. So Wigner had shown that if you have such a matrix where you have an n by n matrix whose C fraction of entries are non-zero, where each of the non-zero entries are chosen from a Gaussian distribution with mean 0 and variance sigma square, then the largest eigenvalue is actually given by the square root of the product of n, C and the variance sigma square. So therefore, this is the largest eigenvalue, the expected largest eigenvalue of the B matrix. And because the largest eigenvalue of the A matrix is related to the largest eigenvalue of B matrix in this expression, so therefore, the largest eigenvalue of the A matrix would be nothing other than this quantity minus 1. Okay? And so therefore, the probability of stability would go to 0 if this quantity becomes greater than 1. Okay? Because it is this square root of NC sigma square minus 1 which is the eigenvalue of A, and we have already said that if the largest eigenvalue is positive, then the system will become unstable. So if this quantity exceeds 1, you would have essentially an unstable system, whereas if this quantity is less than 1, you have the almost surely stable system. And so therefore, it's a very elegant result which says that if any of these quantities or all of these quantities start becoming larger and larger, eventually this product would exceed 1, and at that point the system will become almost surely unstable. Yeah, that's because we are talking about probabilities here, correct? So suppose you come up with all possible networks that you can think of. Okay? Now, as n becomes larger and larger and larger, the exceptions to this would become rarer and rarer and rarer. Okay? But that does not mean that you will not be able to find a few exceptions to this rule, and that's very important actually. Okay? So what May is saying is that if you looked at the ensemble of all possible networks having size n, connection density C and interaction strength with a variance of sigma square, most of this would actually be unstable, but it's not ruling out the possibility that you'll be able to find a few rare exceptions, but these few rare exceptions would become extremely small, rarer and rarer, very hard to find simply by chance, as long as your n becomes very large. So as n becomes larger, these exceptions are becoming very few on the ground. Okay? Now, it's important that you ask this question because eventually we'll find that this in fact turns out to be a possible resolution of this whole paradox. Okay? The fact that there are exceptions, but these exceptions are extremely rare. Okay? And of course, the question is then how does Mother Nature figure out how to find these rare exceptions? Because if you were just trying to find this at random, you'll never find it for a sufficiently large network. Okay? So, going back to May's argument, he said that if you now look at the probability of stability of the network as a function of any of these quantities, you would find that there's a transition from almost surely stable to almost surely unstable as you increase any of these quantities. And in fact, this helped explain the paper of Gardner and Ashby, which had come out in 1970, where they had in fact shown numerical simulations which shows that the probability of stability of randomly constructed networks essentially goes from 1 to 0. Okay? So, this is just given in terms of percentage. So, that is why it goes from 0 to 100. So, actually it should be 0 to 1. So, it just sharply decreases as you increase the connection density, and the sharpness of this transition increases as the system size is increased. So, with bigger system sizes like with 10 nodes, you would see that the probability of stability would almost suddenly go from 1 to 0 around a connection probability of 13%. So, obviously people started debating about this result the moment it came out. In 78, a field ecologist called McNaughton in fact came up with some empirical support for May's result. So, essentially he showed that if you look at grasslands of the Serengeti, then there seems to be some kind of a inverse relation between the connection density and the number of species that you have in the system. This is of course an indirect evidence, because according to May's result, it says that if n is large in an ecosystem, the only way that you can support such a system is by correspondingly decreasing C. Okay? So, he does not say that large diversity is not possible. He said that large diversity is possible, but only at the cost of lowering the connection density. Okay? So, you can increase any of these quantities provided you correspondingly decrease the other quantities such that this condition is satisfied. Okay? And so, therefore, that is precisely what McNaughton showed. McNaughton said that look, if I say that sigma square is roughly the same across all of these grassland ecosystems, then n times C is a constant. So, therefore, n would be inversely proportional to C, and that is what he is showing using his field data. Okay? But as you might imagine, there was a huge pushback, and there were a lot of ecologists jumping quickly into the fray and pointing out that look, we really don't believe in all these mathematical arguments. Clearly, this is fallacious and so on. So, part of the controversy erupted from the fact that when mathematicians talk about stability and when ecologists talk about stability, they are often meaning very different things. Okay? So, Stuart Pym, an ecologist, actually in 1984 wrote a very wonderful review called Complexity and Stability of Ecosystems, where he pointed out that when someone talks about stability, you better make sure what kind of stability that person means, because it could be any of these. Okay? It could be global stability, which is basically a question about, so it could be local stability like what Robert May had talked about, that is, does the system return after a small perturbation about its equilibrium. It could be global stability, where you are asking a question about the size of the basin of attraction of the equilibrium, that is, starting from any point in the system, do you go to a particular equilibrium or not. It could be something which technically is known as resistance. So, like how hard is it to change the system if you give it a perturbation. Resilience, which basically says how quickly does it go back to its equilibrium once you have disturbed it. And variability, which is basically saying that what is the variation in the density over time, usually measured as a coefficient of variation, that is the ratio of the mean to variance. Now, the biggest challenge placed in front of the wider acceptance of May's result in the ecological community was, of course, his assumption of randomness. So he, of course, did that so that he could invoke this elegant results of Wigner, but ecologists quickly pointed out that, look, networks, especially in ecology, are not random. They have various patterns. So, your result may be at fault, and because of this assumption of randomness. So one can ask, how does assumption of various kinds of topological structures affect dynamical stability? Until about 98, even though you knew about all these challenges, there's nothing much you could do, because the only models available for networks were either the random network, which May had already assumed, or the regular networks, which ecologists and mathematicians all agreed was a very bad model for ecological networks. So that's how things stood. But once you had all these other kinds of models coming up, like small world network, scale-free network, then people started jumping into the fray and asking, do you have evidence for these kinds of structures in the ecological systems? So in 2001, Jose Montoya and Ricard Soule did analysis of several food webs and claimed that they were showing evidence of small world, in particular high clustering. Okay. But as with everything that you get from the real world, things are not quite as clear-cut as it seems. So it was challenged the very next year by work done by Neo Martinez's group, where they analyzed a much larger set of food webs and said that, look, there is not that much evidence that in general food webs display any small world topology. Yes, you can find evidence for it in a few, but overall there doesn't seem to be too much evidence of this. So we can ask this, of course, as a theoretical question, that suppose you have taken a network and you impose a small world structure on it, does it affect its local stability if you just do an argument a la May? So it turns out that it actually does not. So here we have shown the probability of stability as a function of connection density, and you can see that as you go from a regular network to a random network, pretty much the transition happens exactly at the same critical value of the connection density. What does change is that the transition becomes sharper and sharper as you go from a regular network to a random network. So it's the qualitative nature of the transition, that is how sharply does it decay, which is changing, but not the value of the connection density at which the change happens. So May's result was primarily related to this critical value. May does not say anything about how sharp this change would be. So from that point of view, May's result holds true whether you have small world or not. So if you're interested, this actually relates to some fairly interesting properties of how the distribution of eigenvalues of a matrix changes from something which was described by this circle in the case of a random network to something which starts developing lobes along the real axis in the case of a regular network. So it has all interesting properties of its own, but sticking to the question of May's stability diversity relation, we can now ask, what about scale free? Again, the same group, Montoya and Soule, claimed that at least one food web seemed to suggestive of a power law distribution. But again, this was challenged by Martinez's group, who actually did a much better job and showed that it actually follows an exponential distribution and not a power law. Again, you can do theoretical studies, and roughly what it, to cut a long story short, again, scale free does not seem to be suggesting any changes in May's result as a whole. And so you can ask, so then how can complex networks be robust at all if structural changes in the network does not seem to be affecting the result of May? Well, notice that so far we have been only focusing on structure. We have not really looked at the dynamics as a whole. So suppose you now bring into the mix the fact that ecological networks typically don't occur full blown in nature. You have a network gradually evolve over time through species coming in and making a space in an already existing ecological network. Sometimes they're successful, sometimes they're not so successful. So you could have a new species coming in, which, if things go right, would now find a place in the network. So now it becomes a new node with its own connections. But many times what happens that the node is unsuccessful in making a niche and it gets wiped out. Okay? And so you have this community assembly where over extremely long times a network starts growing from maybe just a single node to 2 nodes to 3 nodes and so on, eventually becoming the extremely complex kind of networks that we saw in some of the pictures shown earlier. Okay. At the same time, of course, you also have dynamics of networks where species keep evolving, the population densities keep evolving, and that can of course affect network evolution at local scale. So for example, you could have predator adaptation or prey switching, where because the population of a particular prey species goes down, its predator decides to switch its attention to another prey which was much more available. Okay. So locally you would see that certain links would become temporarily stronger or weaker depending upon how its population is affecting the ability of its predator to find it in the environment. Okay. So this principle of how ecological networks are assembled has been looked at, of course, in ecology, where the famous ecologist Wilson has actually compared this phenomenon of how a gradually ecological network is set up with the process by which you solve a jigsaw puzzle. So, so Wilson has this wonderful picture in one of his books where he says that how or what kind of form an ecological network will take depends pretty much on the sequence at which different species come in. So for example, suppose you have species A existing in an ecosystem. Now suppose species B comes in and fits with the niche, set in place by the presence of species A, that in turn makes a niche possible for another species D, which can then come in and prosper in the ecosystem and so on. But now suppose before B comes in, another species C comes in and occupies this niche, it can prevent the entry of species B or species D in subsequent times. So in other words, what kind of network you actually see in place after long times is very much dependent on history. Which node came after which node? Okay? It's not given. Okay? You cannot ignore history and start talking about the properties of the networks that describe this ecology. And so one can actually come up with a very simple model which actually takes this into account. So let's say you start with a single node, you add another node with some given number of links which is given by some distribution and a randomly chosen interaction strength, and you check the stability of the resultant network. Okay. If it is unstable, you remove one of the nodes at random and you analyze the stability yet again. If it is stable, you add another node and you keep doing this. Now compare this with the other kind of network evolution process that we had seen in our course, namely the preferential attachment. So there what we were doing so this part was more or less the same. So you, at every step, you were adding a node with a random number of links, but you didn't have interaction strengths, because that's a new thing. But what you were doing you were adding it to other nodes. And I said that if you had chosen this other nodes that you add to it purely at random, it would result in a Erdős-Rényi random graph. Okay. Now the additional step you have over here is the fact that at every step you are trying to check whether adding this node resulted in making the overall system unstable or not. Okay. If it is unstable, you say that an extinction event will happen and this will result in one of the nodes becoming extinct. Okay. Now sometimes what will happen is when you add a node, it would result in the network becoming unstable. But because the node that you eliminate is chosen at random, eliminating a randomly chosen node will not automatically bring it back to the stable situation. So you might have to eliminate many more nodes before you again hit stability. Okay? So you will have what is known as the extinction cascade. Okay? So typically a run of such network evolution will look like this. Initially the network size will just keep growing as you keep happily adding more and more nodes, but eventually at some point it suddenly becomes unstable. So at that point you start eliminating certain nodes. So under lucky circumstances, just deleting one or two nodes would again get you stability, but occasionally, as you can see over here, in order to regain stability you will have to eliminate many more nodes. So in this particular situation, for example, you have to eliminate quite a few nodes to go back to stability, and sometimes you actually have a regressive step where you go down to numbers below what is expected from maze results. So this is basically the line which, since you know what is your connection density and since you know what is the diversity of your connection strengths, because you know the nature of the distribution from which you're choosing your interaction strengths, so the maze theory would actually tell you that your network should stabilize about this value. Okay? That's of course pretty much what happens at extremely long times, but you would see that there's this steady fluctuation which occurs about this value predicted by May. Now, the important thing is that exactly as May predicted, you have the conclusion that if you decrease your interaction strength, so that means decreasing the diversity of the interactions, decreasing the variance of the distribution from which you're choosing the connection strengths, you can of course stabilize your system at larger and larger average number of species. Also, exactly as McNaughton had shown, there is a reciprocal relation between n, c and sigma. Okay? There's also some interesting behavior in the fact that the randomness in this network is actually showing evidence of long range memory. But the surprising fact is that from the point of view of variability and resilience, so remember what variability was. It was basically saying that what is the coefficient of variation of the individual populations as a function of the mean number of species. So this shows that the coefficient of variation is actually coming down as you increase the diversity of the system. So in that sense, it's actually more robust because it's less variable. The more the number of species, the less the populations fluctuate. And moreover, it's also more resilient because it's coming back now to its equilibrium faster if you have more species. Finally, if you look at the distribution of the extinction cascades, so if you ask, do larger networks have smaller extinction cascades? Yes, it turns out that you have smaller magnitude crashes if you have networks having larger mean number of species. So from that point of view, there's also increased resistance. So turns out that starting from a framework which was pretty much same as the one set by Robert May, namely we are looking at local stability, we seem to have somehow come up with networks which are less variable, which are more resilient, and which are more resistant. So in other words, they are robust from the point of view of field ecology. And so the question is, how did the system manage to actually find out networks which essentially are robust, even though a random search would have not been able to turn these up? So you can think of the process as something like an evolutionary search. Okay? So along the vertical axis, we are essentially increasing the complexity of the network by increasing the number of nodes. And at each level, I'm showing a schematic diagram which shows what is the set of all stable networks in the space of all possible networks for that particular n. So for very small values of n, of course, almost any network you can think of would be stable. Okay? As n increases, the size of this set gradually decreases until at large n, it occupies such a small space that it will be very hard to find it by trying to search for it without any knowledge. Okay? So if you just take this kind of a network and if you just ask, okay, what are the networks which are actually stable given this n, it will be very hard to find them. But that's not what is being done when you are evolving a network in the manner that I just described. So you are doing something like an evolutionary search where the trajectory of network evolution actually tries to always keep itself within this set. So as it grows, as long as it's within this set, everything's fine. The moment it goes out of this set, it then starts going down this vertical axis to try to find itself back into this set all over again. And because as it keeps going down, the set gradually increases, it's almost guaranteed that if you go down enough down the vertical axis, you will always hit the set of all stable networks. So then you start evolving once more up. Okay? So in this fashion, you can actually over time find yourself in that sweet spot where you have very large n, but you belong to that very small set of ecological networks which happen to be stable even though they have a very large n, c and sigma. And so the implications are that if you introduce explicit dynamics and complex structure network, that may not change this relation that you have between network stability and complexity, but by looking at the history of network evolution, by concentrating on the dynamics of networks, you can actually explain how complex yet stable networks can evolve. And so we end with a cautionary note that sometimes looking at the network as it is today may not actually tell us too much about why it has these dynamical properties. In order to understand why a network actually seems to be persisting despite theoretical results, you might have to take into account the history that it went through, the evolutionary process that it underwent in order to reach the state that we see it in today. In other words, taking snapshots may not be adequate when you're trying to understand networks. Okay? So I stop my brief tour of networks at this point, and I hope that it actually gave you some appreciation of the large variety of topics that are subsumed under this field. So you can, given your favorite network, you can study its structural aspects, you can study its dynamical aspects, you can study its evolutionary aspects, and how it relates to its function. Okay, so with that I end, and as I mentioned at the beginning of my talk, if you would like to have more details, you can always go over these slides which I put up in the assistant biology course.